Hello, my name is Thomas Dolan, and I'm here with Julie Kirkpatrick, and we are going to talk to you about our Kaggle competition project. So first, I'd like to go through an overview of what we're going to talk about. I'll talk a little bit about loading the data and some of the issues we ran into, what we did to fix that. Julie and I will both talk about some of the feature engineering we did. I'll talk about the feature encoding we did to process our data frame prior to feeding it into a model. And Julie and I will both talk about the modeling methods that we used. So first, loading the data frame proved to be quite difficult because it's very large. So one of the things we did to fix that is we did some data type conversion. So I created a separate notebook over here where I loaded in the original data frame. And I looked at each individual column, took ranges, things like that, and I got an idea of exactly what type of the categories each should be. So I went ahead and cast them as categorical variables, and we got some data frame size reduction here from 5.5 to 3.9. I then went through and changed some of these objects to booleans. That saved us quite a bit of space as well. We went down to 2.7 gigs. And then after that, we felt like we were good to go. So I used a little function here that created a dictionary that we could use when we were reading in our CSV that would automatically convert the data types. It's a lot more memory friendly. So that I did here. You can see the dictionary is right here. And then one last thing is some of these couldn't be converted in the read CSV function, so I had to go through and actually convert them after reading the CSV. And a little note, we did a sample for our training, 500,000 samples. We wanted to keep it kind of small.
50,000.
I'm sorry, 50,000 to kind of keep it manageable size. So you'll see DF, that's a name for our train data frame, and then test is our test data frame. And with that, I will go ahead and pass you off to Julie, and she's going to talk about how we dealt with our NANs.
So we had a lot of columns to start with. So we wanted to see what columns were missing a lot of data. So we made this little function that has a threshold. And if you were missing more than this amount of data, then we were going to drop you. So there's our output. You can see we had a number of columns that were missing quite a lot of data, and we decided to drop all of those. Every now and again, you're going to see that print shape. That's just to make sure that our test shape and our training shape are very similar. The reason the DF shape is one higher is because it has the has detections target still applied to it. The next thing that we tried to do were we were originally dropping rows that had NANs in them. Well, we found out that we can't do this because you have to still make predictions on the test data, even if it has a NAN somewhere. So we decided to use fillNAN instead. We made a little function that will fill in the NANs with either an unknown if it's a categorical data or the mean if it's numerical. And then we just ran that for both the test columns and the training columns there and there.
Great. Thanks. So next, I'm going to talk about some of the problematic columns that we had, things that we needed to fix. So we did this kind of in order here. The first thing we did is we wanted to find columns that had a high skew. So skew meaning many of the values in that column took on one specific value. We found that we figured that columns like that were probably not very predictive, so we wanted to get those dropped. So we wrote a function here to report those. So we can see that, for instance, your product name has 98% of the values take on one specific value. So that's probably not super predictive. So we went ahead and dropped those. Again, our data frame is in good shape. So Julie's going to talk to you about how we dealt with our categorical column uniques.
So with our categorical columns, with the encoding that we wanted to do later, if it had a lot of unique values, that was just going to make our data frame really, really big because each category unique value was going to get its own column. So we obviously did not want to make 8,500 plus more columns. So we ended up looking at which ones were the highest value uniques, and we did that for both the test and the training data. Back when we were dropping the rows, we had some that were no longer used. Their value was 0, and we ended up dropping those, but since we changed from drop NAs in the rows to fill NAs, that wasn't really a big deal anymore. You can go through that.
Cool. Yeah, and just briefly to touch on what Julie's mentioning is anytime a categorical has a lot of unique values in it, when we do one-hot encoding later, it's going to increase the dimensionality of our data frame substantially. It's going to add a ton more columns. So we wanted to make sure that our column counts were about 100 max for unique values for the columns. So next, yeah, so with that in mind, we wanted to address AvSig version had about, I think it was, yeah, 9,000 or so unique values that it took on for categorical. So one thing we did is we transformed that column into a count of each, of how many times that value was found in the data frame. So for instance, if the AvSig version was 3.0, we went through the data frame, we saw how many times did AvSig version take on the value of 3.0. If it took on maybe, if there were 10 occurrences of 3.0, we now made that attribute 10 instead of 3.0. And so we have counts here instead. And we wanted to graph this out to see if there was any sort of correlation with HAZ detections. We didn't see any specific correlation, so we just left it as is, as just a count, and we left that column the way it was.
Our next highest number of unique categories was this OS Build Lab. So we saw with the value counts that there were some that had a whole bunch of them. The most popular category had 3 million. So we wanted to visualize it in the same way that we did with the AvSig version. And you can see that there are very few very popular OS Build Labs. Most of them are not super popular. So what we did is we changed the categories to be either one of those 4 popular OS Build Labs or other. And we did that with the .apply function. And then you can see when we do our value counts, we have 5 categories. We did something very similar for the next highest one with 475 unique values, the Census OS version. We visualized it. We saw that this one was less grouped up, but still fairly grouped up on the low end. And so we put, I think, a 3%. If you didn't have more than 3% of the population, then you would kind of get lumped into this other category. And that gave us a lot smaller number of unique values.
Those are listed right here.
Mm-hmm. And then
go ahead.
Then our next highest one was 120 unique values, and we were okay with that.
Great. So another type of problematic column is redundant columns. So if a type of column encodes basically the same idea as another column, then it just adds redundancy to our data set and it could throw off our model. So for instance, census internal primary diagonal size in inches, and it corresponds pretty well to horizontal and vertical. So we don't need to keep all 3 of those. So we did a heat map here, visually picked out some high correlated or highly correlated columns, and then we dropped those correlated columns. We just kept one of them. We did that with both our train and our test data frame, again, to make sure that our shapes were still squared away. So Julie, you want to talk about transforming the continuous columns?
So you can see that we've gone from like 80 some columns down to 43. So we've cut out a lot. With the continuous columns, you want to be able to deal with them in multiple different ways. You could discretize them into different bins. You might want to apply a log transformation, and we wanted to be able to easily visualize this data and then make a decision based on what the data looks like. So we made a little function that supplies you with a graph of the data and then allows you to make a decision based on that data, stores that decision, and then at the end actually completes all of those decisions for both our training and our testing data. So that's an example of when we'd want to cut that right down the middle and say, are you low or are you high? Sometimes we would just drop it. This was something that we didn't feel, it was so skewed, we didn't feel like it would have an impact. This one we did a log transformation on because it was skewed, but not as extreme. And then there were some that we did nothing to. So I think city identifier, which is that one, we didn't do anything to. We just kept it as is. And you can see these go in order from very, very high range to lower range. So the range is getting smaller as we go.
So once we dealt with our continuous variables, well, actually I should mention, here's an example of a log transformed plot here. You can see the range is a lot tighter. I think the range before was in the thousands. So we have a lot tighter range. Okay, so next we have all these categorical variables that we can't feed in to a model. So we wanted to do one-hot encoding. One-hot encoding translates your categorical variables into additional columns that are just Booleans. So it adds a lot of more dimensionality to your data frame, but that is necessary if you want to keep those attributes. So we just went ahead and did that using the pandas get dummies function. And after we did that, we went ahead and, well, before we did that, we concatenated the two data frames. This is really important. You concatenate the two data frames so that when you apply one-hot encoding, you still maintain the same amount of columns in both the train set and the test set. So we went ahead and did that. And once we were done with that, we had a data frame that was ready for processing with our machine learning processor. You see all these columns here. It's like a sparse matrix of Boolean values. A lot of these are zeros, but this is what will ultimately be fed into our model, minus the machine identifier, obviously. So, Julie, you want to kick us off on modeling?
Yeah, so we tried 3 different types of models, and when we tried to fit our very first model, we ran into some interesting errors. The first one was that our avsig count was too high of a data type, so we had to downcast it to a float 32 instead of a float 64. And then for some reason we had an infinite value in our display resolution horizontal, so we just ended up dropping that column because we didn't want to deal with it. The first model that we tried was the logistic regression, just because it's really good for the categorical type data. And our model score was not very good. It's just a little better than random guessing. So then we tried k-nearest neighbors, thinking that we might get something better. Our score was a lot higher, but we're probably overfitting. We ran a predict proba on the full data set and then just looked at the first 100 probabilities. And you can see that the probabilities there are either 1, 0, or 50%, which felt very weird to us. So we wanted to look at the logistic regression to see what those probabilities looked like. These were a lot more varied in like digits, but you can see that they're all very close to like 0.49, 0.48, and those would all go down to no, 0. So both of those we weren't super comfortable with, so we scoured the homework and notes and tried linear discriminant analysis. This gave us a score that was in between of 0.6, and then we ran it on we ran predict proba on the test set, and these probabilities we felt a lot more comfortable with. So we submit these to Kaggle. We got a public score of 0.58 and a private score of 0.47, which aren't very high, but that's okay. We're not experts at this. Yeah, so there's probably a good number of reasons why our models weren't super great. One is probably that our training set sample was pretty small. It was only 50,000 out of the 8 million plus data items we had to work with. If we were going to run this all again and take the time to run all of our models again, which would be quite time intensive, I would choose a much higher number for our sample size. Other reasons that our model might not be amazing, as we did end up dropping quite a large number of columns, about half, maybe a little bit more than half. We started out with 80, and I think we ended up with about 40 some. So there might have been some things that were quite telling in those columns that we ended up dropping.
In addition to that, some of our transformations on continuous variables, we did notice that some of those were probably should have been identified or categorical variables. So that probably wasn't super effective, and it probably skewed our model. In addition to that, we were using 3 pretty rudimentary models here from an introductory data science class. So when you look through the kernels in the actual competition, competitors are using much more sophisticated modeling techniques and tuning hyperparameters and things like that. So, but I do think with practice, maybe our next competition, we will do some, be able to use some more sophisticated models once we wrap our heads around it, and we'll be able to probably get a higher score from the modeling as well. So with that, I think, Julie, did you have anything else to add?
No.
No. So that's that was our Kaggle competition submission, and thank you for listening.
All right.